Dr. K.S. Ramakrishnan is working as an assistant professor, School of Education, Tamil Nadu Open University, Chennai 15. He has been teaching science education, environmental science, educational technology and research methodology in various colleges of education and Tamil Nadu Open University for the past 9 years. He has guided so many M.Ed, M.Phil and PhD students. His current research areas are environmental education, educational technology and media and communication. He has conducted various workshops on ICT usage in education, Wiki Educator, e-content development, and educational research methodology. He had attended many online workshops on Moodle, learning analytics. He has published 6 books and many articles in national and international journals of repute. He regularly gives plenary and keynote speeches on environment and ICT related issues at various national and international conferences. He has delivered 28 episodes of the program Pudiyodor Ulagam at All India Radio, Chennai, related to various new developments in science and technology.
Welcome to UGC program. In this episode of Environmental Science, we are going to discuss about the atmospheric stability. So, in this episode, we will discuss about the dispersion of pollutants, the lapse rate, the temperature inversion, the atmospheric stability, the classification of stability and plumes, the type of plumes. So, all that we are going to discuss in this episode. And first of all, air pollutant cycle, to what extent or how the air pollutant are cycling. See, they are emitted from the source and they are transported through various phenomena, and then they are diffusing or concentrating on somewhere, and then they are deposited onto vegetation, livestock, soil, water or escape into space. So, therefore, where the pollutants are produced, they are gradually following all the cycle and again they are settling down as deposition in the form of vegetation, livestock, soil, water or some small amount may escape into the atmosphere also. And the first phenomenon, dispersion. Dispersion means how the pollutants are dispersed into various places, particularly into atmosphere. See, the dispersion is depending on the turbulent velocity fluctuation. See, the wind velocity that is fluctuating, and therefore, the dispersion, the more the velocity or the more the fluctuation or more the turbulence. So, naturally, the pollutants are dispersed fastly, and then diffusion due to the concentration gradients. See, the diffusion means the material, they are going from high concentration to low concentration, and therefore, more the gradient, more the diffusion takes place. And the aerodynamic characteristics of the pollution particle. So, what are they? The size of the particle, the bigger the size. So, depending upon the lesser the diffusion, and the shape and the weight, because the gravity is also playing a major role, and therefore, the aerodynamic characteristics, that is the size, shape and weight, they are also playing a leading role. And first let us discuss about the atmospheric stability. See, the atmospheric stability means the resistance of the atmosphere to vertical motion. That means, the pollutants, if the atmosphere is resisting to move high, because generally they try to move upwards, and so to what extent the atmosphere is resisting them, that is the resistance, and the stable air resists the vertical motion. That means, if the air is stable, then the pollution particles, they cannot move upwards, and therefore, naturally they can move sidewards. So, the stable air is resisting the vertical motion and unstable air encourages the vertical motion. Therefore, if the air is stable, then the motion will be horizontal. If the air is unstable, the motion will be vertical. And it is the lapse rate. So, the lapse rate that is the decrease of temperature with height. That means it is generally denoted by gamma. So, the gamma is equal to minus dt by dz. That means the rate of change of temperature with respect to the height. So, here T for temperature, Z for height, and the lapse rate, the decrease of temperature. We know that as the height is increasing, the temperature decreases, and therefore, the rate of change of temperature, that is called the lapse rate. And the environmental lapse rate gamma, it is in the order of 6 Kelvin per kilometer or 6 degrees centigrade per kilometer. That means, for every kilometer rise above, 6 degrees are coming down. That means, if the temperature is 30 degree in the ground, then if you are going 1 kilometer above, then it will be around some 24 degrees centigrade, and here it is represented by Kelvin and the symbol gamma. So, the lapse rate is dt by dz, and there are two kinds of lapse rate we are going to discuss in this episode. Before that, let us discuss about the adiabatic process. Adiabatic process means there is no heat exchange, that is between the system, and therefore, one is a system and another is the environment, and if there is no heat exchange between the system and the environment, then that is called adiabatic process. So, adiabatic process means no heat is gained or lost by mixing with the surrounding air. So, sometimes they are called the parcels of air, and if there is no heat exchange between two systems, that process is called adiabatic. And GD, dry adiabatic, D for dry, dry adiabatic lapse rate, that DALR. So, what is dry? The rate at which unsaturated parcel cools when lifted. So, see, actually the pollutants, they are in the gaseous state, and therefore, the dry adiabatic lapse rate means the rate at which unsaturated, that means they have not attained, the water vapor has not attained the saturation point, and unsaturated parcel cools when it is lifted, that is called dry adiabatic lapse rate. And the value of dry adiabatic lapse rate, that is from 5.5 degree Fahrenheit per 1000 feet, or it is around some 9.8 Kelvin per kilometer. So, this is one factor, dry adiabatic lapse rate. And the next one, moist one. The moist adiabatic lapse rate, it is for saturated air. So, when air rises and cools, so gradually that the air is cooling down, if dew point is reached, we know that the condensation occurs. So, once it has started condensing, the energy is released with condensation, and therefore, we know that condensation means from vapor state into liquid state, and therefore, when there is a change of state, then the latent heat that will be released. There are two kinds of latent heat, one is the latent heat of fusion and another is the latent heat of vaporization. And so, when water is converted into water vapor, then it is taking heat, and when water vapor is converted into water liquid, then it will release the heat, that about is called the latent heat of vaporization. And therefore, here the water vapor that is converted into water, and therefore, the energy is released. So, it is releasing the energy into the atmosphere, and therefore, the atmosphere is warming. And now, we are defining the second lapse rate, that is saturated adiabatic lapse rate. Why it is saturated? Because the water vapor has started condensing into water, and that is the rate at which the saturated parcel cools when lifted, and generally its value is from 4 to 9.8 Kelvin per kilometer. And therefore, now the whole process of the stability, it depends upon the dry adiabatic lapse rate and the saturated adiabatic lapse rate. So, the moist adiabatic lapse rate, the parcel becomes warmer than the surrounding air and it continues to rise, that is free convection, and eventually reaches colder air aloft, cools and stabilizes at a new level. And therefore, the air parcel that goes on lifted, and so at one point it will start condensing, and so it is exchanging heat, and so it will become warm, and so again because of the temperature increase, so gradually that it will be lifted. And now it is depicted by this diagram, and see here in the troposphere, that is from starting to, that is here the y axis, the height 0, 20, 40 etc., and here the temperature. So, it has started from some 300, actually it is represented by Kelvin. We know that some 27 degrees centigrade, that is equal to some 300 Kelvin, and so 300, 280, 260, 240, like that the temperature goes on decreasing. And now look at the troposphere. In the troposphere, there is a decrease in temperature. At what rate? Minus 6.5 Kelvin per kilometer, and therefore, here it is cooling because the temperature is decreasing. And here the point of inversion, and so at one point that will happen around some 18 kilometer, and after that you see the temperature starts increasing. So, that will happen in stratosphere because the heat is produced due to the radiative heating, that means the ozone conversion. And again around some 50 kilometer, again it is switching over, and again when it is entering the mesosphere, and again the temperature starts decreasing, and therefore, there are 3 zones, and here the temperature decreases, and then the inversion, and here the temperature increases, and again the temperature decreases, and what rate? Minus 3 Kelvin per kilometer. And the atmospheric lapse rate and stability. So, how these two values are related? And already we know gamma is equal to minus dt by dz, and it is a formula G for acceleration due to gravity, and here it is the specific heat capacity, C for specific heat capacity at a constant pressure, and that is equal to 9.8 Kelvin per kilometer. And now here we are going to discuss about 4 conditions. The first condition, dt by dz, that is greater than gamma, that is unstable, and here you look at this portion, and here it is unstable. In this portion you see this portion is unstable because the rate is greater than gamma, and the second portion dt by dz is equal to gamma, that is neutral. So, in this portion, see, you look at this one and this one, both are almost parallel, and that means that the rate at which the atmosphere is cooling down, that is equal to the gamma neutral, and therefore, this region, and therefore, here it is unstable and here it is stable, and third one minus dt by dz is less than gamma, that is stable, and the fourth one dt by dz is greater than 0, that means the value is greater than 0, that means the inversion region, that is very stable, extremely stable, that is represented by this portion. And therefore, there are 4 portions unstable, and here it is highly stable, that is this portion, and here again it will become unstable, and again it will become stable, and therefore, there are 4 portions. And now, the atmospheric stability, it affects the dispersion of pollutants. The temperature bar elevation relationship, the principal determinant of atmospheric stability, and stable. So, when it is stable, there is a little vertical mixing, and the pollutants emitted near surface tend to stay there, that means they are suspended there itself, and the environmental lapse rate is same as the dry adiabatic lapse rate. And now there are 4 common scenarios. So, the stability classes, So, we are going to define the stability classes. They are developed for use in dispersion models. The stability is classified into 6 classes: strongly unstable, moderately unstable, slightly unstable, neutral, slightly stable and moderately stable. And therefore, starting from strongly unstable moving to moderately stable. So, there are 6 classes. And the vertical temperature profiles, we have discussed about the environmental lapse rate. So, and dry adiabatic lapse rate. So, these are the 2 determinants of the vertical temperature profile. When ELR is greater than DALR, that is subadiabatic condition. So, the atmosphere is stable. That means, in this condition the atmosphere is stable. That means, the air is slightly lifted or may not be lifted, and ELR is very greater than DALR, then the inversion region and very stable atmosphere. And the third one, ELR is equal to DALR, the atmosphere is neutral, and ELR is less than DALR, superadiabatic condition, the atmosphere is highly unstable. And depending upon that, the shapes of plume means the amount of the volume of pollution, the shape of the pollution, and that we are calling as plumes. It depends upon the atmospheric stability conditions. So, the shape of the plume, that is decided by these temperature profiles, and so these are called plume. That means, the pollution, the volume or the shape of the pollution, that is called the plume. And so, there are various conditions they are given. And now, let us see this one, the temperature profile, it is stable. That means, it is in the inversion region. At what time it starts? It starts in the early morning. And so, what type of plume? Fanning. And the second plume, that is B, here it is in the near the inversion region, and again it is stable. So, when the sun rises, so here it is highly stable, and now the stability starts decreasing, and therefore, you look at the plume and actually it is fumigation. That means, the upper side is stable, the lower side is unstable, and therefore, it has started that is coming down, and it is called the fumigation. So, these are called various plumes. And now, the temperature has increased. So, the sun rises and gradually the day has started, and now the instability region starts, and now you see there are various different types of plumes, and here one plume, that is looping. That means, it is neither that is both the upper portion and the lower portion both are unstable, and therefore, it is making different shapes. And the fourth one, neutral. Neutral means, it is neither stable nor unstable, that is neutral. And so, here the dry adiabatic rate, and that is equal to the environmental adiabatic rate, and therefore, here you see in this, that is in the evening, the shape is somewhat coning. That means, here slightly it is making the shape of a cone. And the last one, that is it is in the night or the late evening, and here you see it is lofting. Lofting means, the lower portion is stable, the upper portion is unstable. That means, it is exactly opposite to the fumigation, upper portion stable, lower unstable, and here the lower portion stable, upper portion is unstable. So, which portion is stable and which portion is unstable, accordingly the plumes are taking different shapes. And now, the first condition, that is absolute stability, and here the environmental temperature, that is 5 degree centigrade, and here the pollution, and here the dry rate 10 degree C. And you look at the diagram, here it is the environmental lapse rate, and here the dry adiabatic lapse rate, and see in both cases it is greater than this. That means, the environmental lapse rate is less than the adiabatic lapse rate, and therefore, here 10 degree and here 5, and therefore, you look at the diagram, see here the dry rate, that is 10 degree centigrade per 1000 meter, and therefore, gradually it is lifted and here the condensation level starts. So, once the condensation level starts, then what will happen? It will become the wet adiabatic rate and therefore, here again that it is in the stable region. So, you look at the plume and here it is not deviating much and throughout that the shape of the plume that is more or less the same and therefore, when the dry adiabatic rate and wet adiabatic rate they are on the left hand side, then here it is absolute stability. And now, the second condition absolute instability, that means here the environmental rate that has come to the left hand side and here both the dry adiabatic rate and the wet adiabatic rate both are shifted to the right side. Actually, this is a constant rate throughout the day, it is a constant, but depending upon the atmospheric conditions they may vary and therefore, to what extent or in what way that they vary accordingly the shape of the plume. And here the environmental temperature 12 degree centigrade per 1000 meter. So, on that particular day and here the dry rate that is again 10 degree C and here it is reaching the condensation region and after that it will be wet. And now, what is the result? Here it is absolutely unstable and therefore, you take the shape of the plume and it will start diffusing and therefore, accordingly it will take different shapes. Again the conditional stability. Conditional means it is in between the absolute stability and absolute instability and here this is the environmental lapse rate, but in this portion it is on the left hand side and so up to this region the condensation region and here the condensation starts and after that it is switching the direction, that means it is going to the right hand side and therefore, here the dry region it is behaving like stable and in the wet region it will be behaving like unstable and therefore, you look at the diagram, the more and more that it is moving above the stability decreases and therefore, it will start diffusing into the atmosphere and therefore, the shape of the plume that depends upon the relationship between the environmental lapse rate and the adiabatic lapse rate and therefore, there are three conditions. So, one is highly stable, highly unstable and conditional instability. And so, these are the three conditions and the diagram that is well depicting what is the relationship between them. And the characteristics of stack plumes, the dispersion of pollutants, the wind, that is one major condition. It carries the pollution downstream from the source. The atmospheric turbulence, it causes the pollutants to fluctuate from mainstream in vertical and crosswind directions. The mechanical and atmospheric heating both present at same time, but in varying ratios and all these affect the plume dispersion differently. So, the plume is depending upon all these conditions. And now, let us discuss about the plume types. The plume types are important because they help us understand under what conditions there will be higher concentrations of contaminants at ground level. And the first one, that is a looping plume, high degree of convective turbulence, super adiabatic lapse rate, very strong instabilities, and it will happen in clear daytime. See, look at the position of the sun, it is in the clear daytime conditions accompanied by strong solar heating and light winds. High concentrations sporadically at ground level close to stack and occurs in unstable atmospheric conditions. So, when the atmospheric conditions are unstable and the wind is also there, and so it is taking the shape of the loop, and therefore, here you look, it is taking the loop and therefore, it is highly unstable. And the coning plume, stable with a small scale turbulence and overcast, moderate to strong winds, very strong winds, roughly 10-degree cone, that means the angle of the cone and that is around some 10 degree, and the pollutants travel fairly long distances before reaching the ground level in significant amounts, and that means you look at that it is taking a long distance, and therefore, after long distance they will settle down, and you look at the previous one in a very short distance they will settle down and occurs in neutral atmospheric conditions. So, it will happen in neutral atmospheric condition. You look at the graph, it is a neutral condition. And the next one, fanning. It occurs under large negative lapse rate, very strong inversion at a considerable distance above the stack, extremely stable atmosphere. That means, it is happening in the inversion region and very little turbulence. See, you look at the shape, for a very long distance it is going like a very thin shape. That is why it is called the fanning plume. If plume density is similar to air, it travels downwind at approximately same elevation, and that means it is maintaining the same elevation, and it is happening in highly stable, that means inversion region it will happen. And the lofting plume, favorable in the sense that fewer impacts at ground level, that means it is hardly reaching the ground. The pollutants go up into the environment, they are created when atmospheric conditions are unstable above the plume and stable below. That means, it is happening in the unstable region. But what is the fact? That is downward, this region is highly stable and the upper region that is highly unstable, and therefore, here there is no dispersion and there it is a dispersion, and therefore, it is called the lofting plume, the shape. That means, it is highly safe because the pollutants they are going into the atmosphere, therefore, they may not affect the nearby regions of the source of pollution. And then the fumigation, it is extremely dangerous plume because you look at it is reaching the ground very shortly and the contaminants are all coming down to ground level. They are created when atmospheric conditions are stable above the plume and unstable below. That means, above the plume there is no dispersion, below the plume that is high dispersion. This happens most often after the daylight sun has warmed the atmosphere, and in turn a nighttime fanning plume into fumigation for about half an hour, and therefore, this is the condition of the formation of the fumigation plumes. And now, we can go into the summary. So, in this episode we have discussed the dispersion of pollutants, the lapse rate, the temperature inversion, the atmospheric stability, the classification of stability and plumes. So, the total episode that is revolving around the dispersion of pollutants. So, how the pollutants are dispersing. The lapse rate, lapse means down, lapse rate, that is how the temperature is coming down. The temperature inversion, that means in the atmosphere the temperature decrease and then increase and then decrease, that is the temperature inversion. The atmospheric stability, stability means to what extent it is resisting the air to go above. The classification of stability, that is from highly unstable to highly stable, and plumes, that means the volume of pollution or the pollution particles, what shape that they are making. And we have dealt the types of plumes such as looping, coning, lofting, fanning and fumigation. Now, we are having some question. The first question, define lapse rate. The second question, what is the adiabatic lapse rate? Write the values of dry and moist adiabatic lapse rates. The third question, write the types of atmospheric stability. The fourth one, mention the characteristics of fanning plume. And the last question, which is considered one of the dangerous type of plume, write its characteristics. So, with this we are completing this episode. Thank you.